Hello, everyone. Good afternoon. My name is Giri Venkatila. I'm an Innovation Officer at Bureau of Research, Innovation and Information Transfer, in a short form BRIT. Thank you all for joining us today for NJDOT Tech Transfer Program Tech Talk series. Today, you will listen projects that were showcased in last year research showcase. I hope all you enjoy these talks and gain some insights in these topics. Once again, thank you for joining us today.
All right, thank you so much, Gary. And today we're pleased to have 4 separate speakers who will be presenting research studies that were not presented at last year's research showcase. Before we get started with our presenters, I just want to remind everyone that if you have a question during the presentation, please use the chat box at the bottom of your screen. Professional development credits are available if you stay for the full session, and your name must be included among those who registered today. Each presenter will have will speak for about 15 minutes, and then we're going to keep a short time for Q&A at the end of each presentation. So if you have any questions for a presenter, don't hold it to the end of the entire webinar. Just ask during this presentation. At the end of the webinar, you're going to receive a feedback form, and please fill it out, send it back to us. It provides valuable insight for the Bureau of Research in facilitating future events. With that out of the way, I want to introduce all 4 of our speakers. The first presentation will be by Abolfaz Afshari. Abolfaz is a PhD candidate in transportation engineering at the New Jersey Institute of Technology. His research interests include the application of artificial intelligence in transportation systems, traffic simulation and modeling, and data collection. I'm going to do all of the presenters' bios in the beginning here because we're going to be a little tight on time. The second presentation will be by Mohammed Javad Bazdar, who is also a PhD candidate in transportation engineering at NJIT. He's actively involved in research at the Intelligent Transportation Systems Research Center, and his research background includes traffic safety analysis, autonomous vehicle simulation, and the evaluation of transportation system performance through data-driven methodologies. The third presentation will be by Dr. Manuel Zelaya, who received his bachelor's and master's degree in civil engineering from the Polytechnic University of Madrid in Spain, and proceeded to receive a second master's as well as his doctorate from the University of Texas at El Paso. For the last 13 years, he's been working at the Advanced Infrastructure Design as project engineer, senior project manager, and is the leader in the firm's non-destructive testing and evaluation division. And our final presentation will be by Bowen Gang, who is a PhD student at Rutgers University. Bowen in the past has contributed to many NJDOT supported projects, including the Data City Smart Mobility Testing Ground and the Advanced Traffic Signal Performance Measures Initiative. So we have a lot of really qualified and interesting speakers today. And with the introductions out of the way, I'm going to turn it over to our first presenter, Abolfaz. He's going to be presenting Assessing the Accuracy of LiDAR for Traffic Data Collection in Various Weather Conditions. Abolfaz?
Hello, thank you, Ami. Thank you for the introduction. Let me share my slide. So I assume that you can see my slide, right?
We can see it, yeah.
Okay, perfect. Good afternoon, everyone. Thank you so much for joining today's webinar. I'm Abolfaz Afshari, a PhD candidate at NJIT, working under the supervision of Dr. Jungli and in collaboration with Dr. Dejan Besensky from the ITS Research Center. Today, I'll be sharing insight from our study on how well LiDAR-based traffic detection systems perform under different weather conditions. Before we get started, let me give you a quick overview of what we will cover today. First, I'll explain what LiDAR is and why it's important for traffic monitoring. Then we will go over the motivation behind our study and its main objectives. After that, I'll walk you through the study site, the sensor setup, and our data collection methods. We will then get into the accuracy results, looking at how the system performed for different object types in various weather conditions. Finally, we will wrap up with some key findings, recommendations, and a question and answer session. So what is LiDAR? LiDAR stands for Light Detection and Ranging. It's a remote sensing technology that uses laser pulses to create detailed 3D maps of the surrounding area. It works by emitting rapid laser pulses and measuring how long it takes for each pulse to bounce back after hitting an object. This data helps to accurately map distances, shapes, and sizes. LiDAR is widely used in traffic monitoring because it can detect different types of road users like vehicles, bikes, pedestrians in real time. It's particularly valuable because it works well in both daytimes and nighttimes conditions, thanks to its high resolution data. On the right side of the slide, you can see a visual representation of how LiDAR data appears as a 3D point cloud in software. Objects like vehicles and pedestrians are identified and classified based on their properties and spatial positions using a built-in application provided by the company. The motivation behind this study stems from the growing reliance on LiDAR technology in traffic monitoring systems. While LiDAR has proven effective in detecting vehicles and pedestrians in clear weather, its accuracy under adverse weather conditions remains a concern. Our objective was to systematically assess how varying weather conditions such as rain affect the accuracy of LiDAR-based traffic detection systems. We aim to quantify detection accuracy for different object types, cars, buses, trucks, pedestrians, and bikes, and identify areas for potential improvement. During our study, we used a 32-channel LiDAR sensor. It was capable enough for our analysis, but it's worth to mentioning that more advanced versions are now available, like a 128-channel sensor. These newer sensors provided higher resolution and could potentially detect a smaller or a partially hidden object more accurately. We have some new 128-channel sensors, but haven't tested their performance on rainy days yet. I hope we can have an opportunity to explore its capabilities in a future study to see how it performs under similar conditions. For this study, we chose the Warren Lock intersection near NJDOT campus in Newark, New Jersey. We picked this location because it has a variety of traffic patterns and a complex road layout, making it ideal for testing our detection system. We installed a LiDAR sensor with a 360-degree view and a 200-meter range to cover the entire intersection, including surrounding streets and sidewalks. Alongside the LiDAR, we also set up a wide-angle camera to serve as our ground truth reference. This camera provided visual validation for the object detected by the LiDAR. Data collection took place continuously from May 12 to May 27, 2024, with both the LiDAR and the camera running at the same time to ensure accurate comparison. So we collected weather data for this study from Newark Liberty Airport Station. The data included key variables like temperature, humidity, wind speed, and precipitation. To make sure we had a well-rounded data set, we used a statistical sampling method called Latin hypercube sampling, or LHS. This method helped evenly sample each weather parameter throughout the study period, ensuring we had a balanced representation of both clear and rainy days. This way, we could effectively analyze how different weather conditions impact LiDAR detection accuracy. On the right side of the slide, you can see a scatter plot showing the relationship between dew point and humidity for the time period we analyzed. The red circles represent data points with no precipitation, while the blue diamonds indicate period with precipitation. If we look closely, we can see that most precipitation events happen at higher humidity level, typically about 80%, with dew points ranging from 60 to 75 degrees. In contrast, the non-precipitation data points are more spread out, covering a wider range of humidity and dew points. This variation allowed us to assess how LiDAR perform under diverse environmental conditions. To evaluate how well the detection system performed under different traffic patterns, we divided the study area into two sections. Area 1, as shown in the image, included Warren Street westbound, the right turn from Lake Street, and the left turn from Raymond Boulevard, and also a part of the crosswalk. Area 2 covers the right lane of Raymond Boulevard southbound, the entrance to Wycliffe Street, and the crosswalk. In both areas, we focused on detecting fine main object, as I mentioned, car, buses, truck, pedestrian, and bike. We compare each detected object with the ground truth data from the camera to assess detection accuracy under both clear and rainy conditions. Now, let's take a look at the result. These two charts compare the LiDAR detection results with the ground truth data. In both charts, the red circle represents detection on clear day, while the blue one indicates detection on rainy days. Also, the y-axis shows the number of objects detected by the LiDAR sensor, and the x-axis shows the ground truth. So points closer to diagonal line are showing more accurate cases. Starting with the left chart, which shows area 1, we can see the most data points cluster around the diagonal line, indicating high detection accuracy. However, we do notice some slight deviation on rainy days, suggesting a minor drop in accuracy under wet conditions. In the right chart, which represent area 2, the pattern is similar. Data points remain closely aligned with the diagonal, showing that the LiDAR maintained consistent accuracy even during precipitation. This suggests the system performed well across different weather conditions. Pedestrian detection showed more variability, especially in area 1, which you can see in the left chart. The data points are more scattered during rainy conditions, indicating potential challenges in accurately detecting pedestrians when the weather is bad. In contrast, area 2, shown in the right chart, demonstrates better performance. The data points are more tightly clustered around the diagonal line, suggesting improved accuracy. However, we still notice some minor discrepancies during precipitation, indicating that while the LiDAR system performed better here, there is still room for improvement in rainy conditions. Buses and trucks were detected with relatively high accuracy across all weather conditions. Since they are larger and have more distinct shapes, the LiDAR sensor was more effective in identifying them compared to a smaller object, like pedestrian. The detection of bikes shows good accuracy in both areas, as seen in these charts. Most points are aligned closely with the diagonal line, indicating that the LiDAR system effectively detects a smaller vehicle like bikes. However, we do see some deviations, particularly on rainy days in area 1, as shown in the left chart. To assess the accuracy of the LiDAR detection, we use the mean absolute error, or MAE. This metric provides a straightforward way to measure the average error across different road user categories and weather conditions. You can see the MAE formula on the slide, along with the results shown in the chart on the left. In this figure, each bar represents a different road user type, with the overall average for all road users shown in the dark blue color. We have separated the data for each area and also combined them to give a comprehensive view. Looking at the result, we can see that cars and pedestrians typically have higher MAE value, especially on rainy days. This indicates a drop in detection accuracy under wet conditions. These findings highlight how LiDAR performance can vary based on weather and road user type, suggesting that adjustments might be necessary to improve accuracy in adverse weather. Now, on the right side, We have the hourly adjusted MA results. We calculate these values to provide a more detailed comparison by accounting for the different lengths of observation station, which was 160 minutes for clear day and 130 minutes for rainy days. By adjusting the MAE values hourly, we can more accurately assess LiDAR performance under varying weather conditions. For instance, in area 2 on rainy days, the hourly MAE for cars is around 1, meaning that the LiDARs count differed from the ground truths by an average of 1 vehicle per hour. Interestingly, except for one category, that is pedestrians in area 1 during rainy days. All other hourly MA values are below 1, suggesting relatively minor discrepancies in vehicle count detection overall. So while the LiDAR detection can generally be considered reliable in both clear and rainy conditions, there is still room for improvement during rainy weather, particularly for pedestrian detection. This underscores the potential need for further calibration or enhancement of the detection algorithm. We identify a few limitations in this study. One of the main challenges was maintaining consistent detection of pedestrian carrying umbrella or heavy or big items. These objects sometimes interfere with the sensor's ability to accurately identify them. We also observed that fast-moving vehicles were occasionally missed, even on clear days. This was likely due to relatively small detection area we were working with. Another issue was double counting. This happens when pedestrians moved in and out of the sensor fields of view or when they walked in groups, making it harder to accurately track each individual separately. To wrap up, our study shows that the LiDAR sensor is generally effective in detecting vehicles across different weather conditions. However, when it comes to pedestrian, accuracy tends to drop slightly during rainy days. While refining the detection algorithm and adjusting the sensor calibration, we can potentially address these limitations and enhance overall detection accuracy. To address the challenges we identified, we recommend a few target improvements. First, adjust the sensor calibration to better detect pedestrian carrying umbrella. Two, enhance the pedestrian detection algorithm to reduce double counting. Three, develop strategies to more accurately track fast-moving vehicles. And finally, conduct further testing in other weather conditions like fog and snow to validate our findings. Thank you all for your attention. I'm now happy to take any question or hear your thoughts and recommendation regarding this study.
Thank you so much, Abulfaz. We did have a couple questions come through. A reminder, you can use the Q&A pod or the chat pod at the bottom if you have any other questions. The first question was asking about the improvement in the LiDAR technology. Do you think it's going to be mostly a technological improvement, or is it just a calibration that you need to do to get better results?
As I mentioned that right now, 20 channels LiDAR sensors are available. Those sensors are perform better in most situations. And also, so when we have we consider the LiDAR sensor itself just like a point cloud without any other useful information. But the main part of this LiDAR technology is the algorithm that we are using for automatically detect objects. So the calibration and the adjustment of the parameter on those detection algorithms also important, and I think we can calibrate them and make them more accurate.
And what are the costs of using the LiDAR technology?
You mean the cost of the sensor itself?
Yeah, the unit itself.
I'm not sure about that part because it's in our university, someone else handling that area, but I think this is still should be expensive.
Okay. I don't see any other questions. So thank you so much.
Thank
We're going
you.
to move on to the next presentation. That's going to be by Mohammed Javad Bazadar, and it's called Traffic Crash Severity Prediction Using Synthesized Crash Description Narratives and Large Language Model. Thank you again.
Hello, everyone. Can you hear me?
Yes, we can.
Oh, thank you. Hello, everyone. Before starting, I'm sorry a little about my sound. I'm a little sick, so maybe it'd be a little noisy. Sorry for that. Today, I'm going to talk about our project about traffic crash severity prediction using large language model. In this project, I worked with another PhD candidate, Tufajol Hossein, and our professor, Dr. Joanne Lee and Brasilwa Dimitrovich. First, I'm going to talk about why the prediction of the crash severity is important for us, and why we want to predict it so accurate, and what was the problem of the other study and previous study, traditional modeling, what was the gap of them, and why they cannot predict well the crash severity, and what our solution for that problem. And then I'll go through some results, and at the last section, I'll talk about what we're gonna do in future to make our result better. Okay, first I'm gonna talk about a little about the predicting crash severity, why it's important. Actually, one of the most important reason that we predict the crash severity is to find the contributing factors, to actually using this contributing factor to prevention of the severe crashes. And we can use these contributing factors to actually train the autonomous vehicle to behave like in a way that they don't have the severe crashes, the major injuries or fatal crashes. And also we can use this factor if this factor is related to infrastructure, we can use this factor to fix this problem. For example, in a history, if we have a lot of crashes in an intersection, the severity is fatal or injury, we can find the problem and fix the problem. And another two reason is emergency response and resource allocation. I will talk a little more about this in the next slide because most of the paper doesn't focus, actually don't focus on these factors, these reasons for the crash severity prediction. Previous study used traditional modeling like a logic model or classification model, decision tree, random forest. And the problem with those study is the data. Actually, crash reports usually have a lot of missing value. If you are a transportation engineering and you work with crash reports, you will know that it's a mess because the crash, there are different formats of crash reports. Everyone use different formats of words. For example, for a rear end crash, someone says the rear end, someone says it's a front end. Or for the light condition, someone doesn't mention about the light condition. Someone says it's a day or night. Someone says that the lamp was on, it was a light. So we have a lot of missing value in constant, actually the different formats of narrative, different words they use. It's hard for the model to understand it. Even if you just turn the narratives to a structured data or tabulate, you will find out that you have a lot of missing value. As you can see in the right, for example, there is 3 different crash reports. The first one doesn't have anything about the light condition. The second one didn't mention anything about the weather. And the third one didn't say anything about the contributing factor. And in this situation, when you have, for example, 10 million crash records and you want to predict crash severity based on that, you need to just remove the missing value. At the end of the day, you will have just 1 million record. And even if you get a good result from the model, it's not reliable. It's not accurate because you just train the model based on the 1 million of the data. So we find out that with this new technology, large language modeling and AI, that there is a solution for that. Actually, LLM, large language model, can understand the text can get the meaning of the text, not the words. Actually, it doesn't matter that you say that it's a rear end crash or it's a front end crash. The models can understand it. And if there is a missing value with the data, still you can use that record. You can use all the 10 million record if you have it as an input of the model. So even for the structured data, if you have tabulate data that works well, you can turn it to narrative, like what we did, and use an input of the models. So we did actually the same thing. We had tabulate data, structured data about the crash report. So we turn it to narrative and use it the import of LLM. Before going to start to talking about the methodology and the data that we work with it, I just want to give you an overview of the studies that use the natural language processing or LLM for the crash severity. Mostly they use two types of the natural language processing. One is large language model. The large language model actually divided to two category: decoder models that most of you probably use, the ChatGPT or the Llama or the DeepSeek, or the encoder models that they actually a pre-trained model on a big source of the data, and you can use them for the text classification like BERT, Roberto, or Albert. Like we used for this project, we used the BERT. There were a lot of the papers or study that used the natural language processing. Actually, the natural language processing, especially topic modeling methods, they are not pre-trained. They need to be trained from the scratch on the data, and they use words of the topic or text to classify the text to a topic. And you need to just remove all the extra words and just keep the important words and assign a topic to it. So we choose to work with the BERT as one of the text classification model. Our data is 3 million crash record from January 2010 to November 22. And it's a structured data. It's not a narrative, so it's like a table or tabulated. So you export the data from this tabulated data and make a narrative from that. But one important part of our project is that we just export the data about the crash time, date, and location, and environmental condition. It was important for us. We just use this kind of data because, as I said, for example, emergency response or resource allocation, you just have this information about the crash. You don't have all information about crash. For example, you don't, for the initial report of the crash, you don't have information about the age of the drivers, or you don't have information about what was the cause of the crash, or for example, how many cars were involved in the crash, something like this. You have just initial report that when crash happened and where crash happened. So with that information, you can allocate a resource or just have a response for that. We just wanted to use this kind of data to just cover all the reasons that we want to predict the crash severity. The crash record that we had was based on the KABC or crash severity scale. That is 5 category of crash severity: no apparent injury, possible injury, suspected minor injury, suspected serious injury, and fatal injury. We just merged them to 3 categories to just make it more clear for the model to classify them. It's an overview of our data. As I said, it's 3 million records for about 12 years. And for the last 3 years, we do just check that if it's almost the same. It didn't change the percentage of the different category. And as you can see, the data is so imbalanced. So we needed to handle this imbalanced data as well. It's a methodology that we use. We use just first go through the tabulate data and export the data that we wanted from about the data, the location, weather, and everything, and create a narrative of that. Where the narrative includes 6 sentences. The first and second sentence is about time, date, and information about the crash location. The third and fourth is about the traffic information like the speed limit and AADT, and all this information is related to location and the time and the date. It's nothing about the crash. The fifth sentence about the weather condition of the time of the crash, and the last sentence about the facility present at the crash location. For example, there is a stop sign or not, or something like this. And the narrative that we created actually is some kind of, it's so well structured. So if some kind of this information is missing, we know about it, and the code will remove that part of the sentence that doesn't, actually the sentence makes sense. And we use this narrative as an input for the BERT. The BERT will tokenize the sentence and go through the embedding and encoding and the neural network. I will classify the data to that what would be the crash severity of that crash. Another methodology that we use, we found out that the data is so imbalanced. So even with balancing technique we use, still the model will predict most of the crashes like no injuries. So we thought maybe if we use the probability, the class probability of the bird as an input of another classification model, that helps better. It means that, for example, if the crash is minor injury, the bird will predict it if 20%, 25% minor injury, but still give us the result of no injury. So these results used as the input of another classification model can help us that if even 25%, if all minor injury shows 25%, so this classification model can understand it and gives us the result that it's minor injury. We use this methodology too to make sure that the imbalanced data doesn't affect on our result. And it's our result for the BERT and hybrid model. As you can see, we try two different balancing technique to just handling the imbalanced data. Undersampling and oversampling, we use both these techniques for before creating the narrative and after the creating narrative to make sure that it's it doesn't bias the data. The F1 score is not so well, but it's one of the best results that is all paper that use the limited number of this information. And for the hybrid models shows the same result. What the interesting part of that was that, for example, for the BERT model, it took about 2 or 3 days to run the model and give us the result based on our source of the machine and everything. But when we turn it to hybrid model, we got almost the same result, but just in several hours running the models. We didn't expect to see that, but it was interesting to see that. And actually, we are planning to, in future, to make our result better. We thought maybe just adding so much, actually, more accurate information to our narrative would help us to have a better result. For example, we tried to use, again, another LLM model to get an image to text description. It will take a lot of time to go for all the records, but it will help a lot. A screenshot of the location and turn it to a description, add it to narrative, will give us a good result. We tried it, a sample of them, but we don't have the result yet, but we think that that will help a lot. And also adding land use and environmental data to description will help too. For example, that the crash happened in residential area, or there are any kind of park around there, or nothing like railroad. And at the end, we are thinking about, instead of creating narrative ourselves, like just 6 sentences, we can use open source another LLM models to give the structured data to the models, and the models create narratives. It means that we don't need to have all narrative in same format. We can have a more realistic narratives, and they be in different formats. And we are going to use these tips to make our result better. Thank you all for listening to my presentation. Feel free to ask if you have any question. I'm here to answer it.
Thank you so much, Mohammed. There was a couple questions that came in a few slides ago about your data quality. Somebody had asked how your language model handles missing data fields like the weather. I know you kind of touched over that, but can you describe again what the model does when there's the field missing? Does it try to fill it in using inferring data, or does it just skip it completely?
No, it will skip it completely. Actually, there is a narrative, for example, if we have a missing value about the light condition, the narrative doesn't mention anything about the light condition. So in the traditional model, we needed to just remove this record because we didn't have the information about the light. But in here, we don't need to remove the whole record because maybe the record have more important information in it. So we just skip that part of the light condition from the narrative. The narrative doesn't mention about it.
And what percentage roughly of your traffic reports were missing data? Was everything missing something, or some more than others?
Yeah, the problem is that it's not about, for example, you don't know about that how many percent of the data is missing lights. Maybe just 10% of them is missing light, but another 10% missing about the cause of the crash. Another 10% is about the missing about the presence of the traffic facility in there. So it's almost half of them have different kind of the missing value.
Okay. That's all I see right now in the chat pod. Thank you so much for your presentation. It was
Thank you.
wonderful. We're going to move on to our third presentation from Dr. Manuel Zelaya. And that's going to be non-destructive methods for bridge deck forensic assessment.
Good afternoon, everybody. Let me see if I can share my screen. Yeah. Can you see my screen now?
Yes, we can. Thank you.
All right, awesome. Thank you so much. And thanks everybody for attending this tech talk. And hopefully you will enjoy my presentation as well. All right. So I'm going to be, I'm going to be presenting some forensic study that we did on a bridge deck here in New Jersey using non-destructive testing methodologies. Before we start, I'm just going to say a little bit something about AID, Advanced Infrastructure Design. We've been, we are a small company, was a consulting company in New Jersey that we've been working for more than 25 years in the Northeast of the US. We are we're proud to say that we use a lot of state-of-the-art testing technologies, most of them non-destructive, including GPR, ultrasonic, 3D laser cameras, and so forth. We are working with the New Jersey DOT and many other big firms and state agencies in the area, and we specialize on pavement asset management, structural assessment, and forensic studies, and for, like I said, many agencies in this Northeast area. Now I'm going to be talking about the case that I will be presenting. This was a forensic investigation that we conducted on a bridge on Interstate 287 near exit 21A. The objective, because this bridge was going to be going there was going to be some construction going on the bridge, and the issue is that the NJDOT didn't have enough information about the retaining walls. There were no as-built, and we were asked to do some forensic studies to try to identify In this case, we needed to identify the presence of reinforcement of the abutment walls that include the location, the rebar cover depth, both on the longitudinal and transverse direction. And we also needed to identify possible extent of the cracks on the abutment walls, and also the length of some bolts embedded in the on the abutment walls. You can see an image of the, sorry, I'm trying to, okay, there. Let's see if I can, oh, not again. All right. So this was the bridge of interest, and these are the west abutment and the east abutment walls that we needed to investigate. Okay, and we used two types of non-destructive testing methods. One of them was ground penetrating radar, is probably one of the most well-known NDT methods, and another one was ultrasonic testing. GPR, like I said, is a very well-known technology. It has many different types of systems. Some of them are retrofitted to testing vehicles. Some of them are handheld devices. Because in this case, we were just evaluating the abutment walls on this bridge. We use a handheld device manufactured by GSSI, but there are many other manufacturers that have similar devices. And we use GPR to identify the presence, location, and distribution of reinforcement within these walls. The way GPR is being operated, whoever is using the antenna, this handheld device, it will collect the data in the vertical and horizontal direction to try to identify the presence of longitudinal and or vertical and horizontal reinforcement. GPR is a really nice technology to identify especially varied objects, especially steel, like for example, steel reinforcement. And when the antenna is collected or is collecting perpendicular or to the, for example, a steel rebar, you will see that rebar as an inverted hyperbola. So GPR is a perfect tool to identify steel reinforcement in concrete structures. For example, in this snapshot, this is a typical GPR scan that we collected on one of the abutment walls. You can see like 3 distinctive hyperbolas. So each one of them corresponds to a rebar that was located perpendicular to the direction of the data collection. Some of the information that can be obtained from this image is the concrete cover, because we know where the surface of the, in this case, the abutment wall is located. And then we know the distance to the top of the rebar. That's how we can obtain the concrete cover. And we can also measure the distance between different rebars. With this information, it was we collected both on the longitudinal, or we collected vertical and horizontal passes with the GPR, and we were able to identify the presence of the longitudinal and the vertical reinforcement. This information was very important because there were no as-built for these retaining walls. And this information was really needed in order to make sure that the reconstruction on the bridge above was not going to be impacted. Okay, so we superimposed all our findings on as-built, and in this case also like some images, and that was very useful for the DOT to complete the as-built for these abutment walls. These are some of the typical findings that we provided not only like the location of the rebars, but we also build the, like I said before, because we can measure, or we measure the cover, we were also able to identify exactly how deep those rebars, both on the vertical and horizontal direction, were located on the abutment walls. The second NDT method that we use is called ultrasonic testing. This is a kind of a slower operation compared to GPR, but it is a complementary tool to GPR and other NDT technologies. This type of testing, it includes a bunch of sensors that emit and receive ultrasonic waves, and you can back calculate and reconstruct whatever is on behind the surface of the element that you are inspecting. The system that we use, it has about 40 different sensors that they fire and they receive the data at multiple times. And the system already has some software that you can back calculate all that information and try to create images or to identify what is behind the structure of interest. Okay. With this information, or with this device, we can collect what is called different A scans, B scans, C scans, or D scans. That is different terminologies to define what plane you are looking at. In case you are looking at, let's say, a plane perpendicular to the data collection or parallel to the data collection. But just this is only a terminology that, with this device, we can obtain all these different reflections on different planes to identify different, for example, objects. You know, if you want to obtain, for example, river mapping, or if you want to identify if there are any anomalies behind the structure, we can look at different planes of the image that we can reconstruct with this device. These are some of the typical post-process data from the ultrasonic testing device. As you can see, we're looking at different planes like A scan, B scan, C scan, and it was clearly seen the level of reinforcement, and some other features were also observed. Like, for example, this is one of the images under the surface of one of the abutment walls, and this was not related to the reinforcement, but it was, for example, an anomaly that was identified with this device. This is one of the close-up of these anomalies, and with this device, we can precisely identify this type of features that are embedded in this case on the abutment walls that were scanned. Okay. Similar to the GPR findings, we use the data collected with the ultrasonic device, and we, in this case, we identify one significant anomaly buried under the surface of one of the abutment walls, and it was notified to the owner and our client that this area needed to be like further inspected in case, for example, it was associated with a concrete void behind the surface. We also conducted another study on the walls because there were some bolts that were installed inside the walls this was to support some of the beams for the bridge. Okay. And we needed to identify the length of these bolts on both abutment walls. In this case, we also look at the data collected from both NDT systems, ground penetrating radar antenna, and the ultrasonic testing device. Okay. This is one of the GPR samples that we collected on the area that we were looking for those bolts. It was clearly, in this case, you can clearly see the location of I don't know if it was longitudinal or transverse reinforcement in this case, but it was clearly identified the reinforcement. But in this case, we couldn't identify any other feature besides the reinforcement. So GPR in this case was not successful. However, when we look at the ultrasonic testing, we identified some features that we associated to the bolts embedded on the abutment walls. And it was an important finding that, for example, in this case, on the west abutment, the location of those bolts were deeper compared to the east abutment. So again, this information was shared with our client and NJDOT for their inspection. Okay, and to conclude the findings from this forensic study, like I said, we use a couple of NDT methods. There are many other methods, but for this particular application, we believe GPR and ultrasonic testing were the most appropriate. Like I said before, GPR is a perfect tool to identify embedded reinforcement, and it was used to identify all reinforcement within the abutment walls, both vertical and horizontal. We also complemented GPR with ultrasonic testing. With the ultrasonic testing, the reinforcement close to the surface was also clearly identified, but we also were able to identify embedded anomalies that could be either voids or delamination. And the third objective of this study was to identify the depth of these embedded bolts. And with the ultrasonic device, we were able to see at some locations that some of these bolts were deeper on one abutment wall compared to the other one. And I believe this concludes my presentation. And now I will be happy to answer any question if somebody has anything.
Yeah, just one right now. What was the process workflow like for the ultrasonic
Yeah,
testing?
it's not that intuitive compared to ground penetrating radar. With GPR, you can clearly identify those inverted hyperbolas, and immediately you can associate those to steel reinforcement. Mm-hmm. With the ultrasonic device, you need to do some post-processing in the office. Results cannot be obtained on the field compared to GPR. But in the office, there is a process called SAFT that you kind of reconstruct the the ultrasonic reflection received by all the sensors. And then that's how you can create the image at different on different planes. So it's right. Not intuitive. It takes time and it takes some experience to make that analysis. But all that is done in the office.
Okay, that was the only question I see here. So thank you so much, Doctor.
All right, and let me stop sharing. Okay. Thank you so much.
Thank you. And we're going to head into our last presentation, traffic signal phase and timing detection from roadside CCTV traffic videos based on deep learning computer vision models by Bowen Gang.
Thank you, Omid. Hi, everyone. My name is Bowen, and I am a PhD student working with Dr. Peter Jin from Rutgers University. And today I'm going to present one of our ongoing research, traffic signal detection and recognition using computer vision and roadside camera. The presentation will follow this outline. I will first give a brief introduction on our background, motivation, and research objectives. Then I'll quickly go through the literatures in this field that we reviewed. And next, I will talk about our methodologies, describe our data, and evaluate our model. And finally, I'll give a conclusion and some future works for this study. Traffic signal information is important for both traffic users and traffic management centers. From vehicle base, this is important for autonomous driving and some advanced driver assistance system. And from roadside perspective, the traffic signal information can be used by traffic management center or traffic control center in some automated traffic signal performance measure system and some intelligent transportation system, connected vehicle messaging system. While autonomous vehicles can perceive traffic signals using its own onboard camera sensors, the roadside traffic signal data can only rely on the infrastructure upgrade, which is a huge cost. So our motivations are advances in computer vision provides efficient tools for detecting traffic signals using roadside camera that has already been employed in many intersections. And we're trying to use this technology to support ATS-PM and connected vehicle system without the significant infrastructure upgrade. Our research objectives are first, develop and implement methodologies for traffic signal recognition using roadside CCTV camera, and then compare multiple state-of-the-art computer vision methodologies in this field. Most of the previous studies focused on vehicle-based traffic signal recognition. At the very beginning, the researchers used traditional image processing method, including half transform, edge detection, and etc. And then as the computer vision technology and AI technology develops, the two-step pipeline became more standard. Those methods first use some deep learning based method to do the object detection to detect the traffic signal head, and then do the color recognition using either traditional image processing or some deep learning based model. And in recent years, as the computing power grows, end-to-end detection became more popular. That's for the vehicle-based detection. And from roadside, the research studies are really limited. Some researchers use vehicle trajectory detected from roadside camera to estimate the traffic signal state, sorry. In summary, the mainstream in this field can be categorized into two-step pipeline or end-to-end detection. Each of them has its own pros and cons. Two-step pipeline use two separate models for the two separate tasks. It is slower, but it can be more accurate because it's easier to debug due to its separated nature. And the end-to-end detection is more straightforward and simple to implement. And it's also fast to process due to the less number of neural network. However, it is hard to debug and hard to isolate each step due to its end-to-end nature. In our method, we adopted 3 different methods. The first one is a 2-step recognition method. We firstly detect traffic signal head using YOLO V8 object detection algorithm. And then we use a traditional image processing algorithm with HSV color space classifier. HSV stands for hue, saturation, and value. It is the color space that used to simulate human color perception. It is more robust against various light condition compared to other color space that commonly used in computer vision field. However, this field, it requires some manual work to fine-tune the color threshold among 3 different colors, green, yellow, and red. The second algorithm we used was also a 2-step recognition method, but this time we replaced the HSV color classifier with the YOLO V8, with the deep learning based YOLO V8 classifier. So it's more accurate and more adaptive to various conditions. However, since we're using 2 different neural networks, this method requires more computing resources. And the third method we used was a end-to-end model using YOLO V8 object detection. We trained our own end-to-end model so that this method, it takes image frame and it returns the color directly. This is really easy to implement. However, it requires much more labeling effort and it's hard to debug due to its black box nature. One of our strategies to enhance the detection accuracy is that we took advantage of the stability of roadside camera view so that we can predefine a metadata region of interest to filter out those unreasonable or inaccurate detection results from the raw YOLO detection result. The left figure shows the raw detection result. There are some misdetections and users detections. And the right figure shows the result, the result that after we filter out those unreasonable results. To evaluate our method, we use the data from our data city smart mobility testing ground corridor located in downtown New Brunswick. We use 24 hours of video data from 5 different signalized intersections. The left table shows the information of each intersection, and the right figures show how our data look like. Currently, our model reached an overall accuracy of around 85%, with some colors more accurate and some color less accurate. But we consider this overall performance is good, and we can further enhance this performance by enlarging our training data set. And these are our demos. These are demos for our detection method. As you can see, we implemented our methodologies on different intersections and different time of the day. As we detect the signal color, we can formulate them into specific connected vehicle messaging format. And when the traffic signal changes, we can also log the information into ATS PM system in real time. This is our conclusion. This study compared multiple cutting-edge detection methods for traffic signal detection and recognition, and we took advantage of roadside camera to further enhance this detection methods. And currently, our proposed method reached an overall accuracy of 84.7%, and this performance can be further enhanced by enlarging our training data set. And this proposed method also supports real-time traffic signal data logging and transmission for potential ATS PM and connected vehicle applications. This is our reference list. Most of them are based on are focusing on vehicle-based traffic signal detection and recognition. Thank you for your time and attention. I'll be happy to answer any questions.
Thank you so much, Bowen. There was one question asking how many cameras you had at each intersection.
Sorry, let me go back to that slide. For each intersection, we have 2 cameras facing 2 directions. Some of them are, for example, one of the camera is facing north and the other is facing south. And some of them are facing east, some of them are facing west. But basically for each individual intersection, we have 2 different cameras.
And what did you attribute to the differences in the color recognition to? Was it a technological limitation or a camera placement issue?
I think that would be some computing resource issue, because we're trying to implement this in real time, so that the latency is really a big issue. We are trying to balance the accuracy and the processing time.
Okay, I see no further questions here. Thank you so much for your presentation.
Thank you.
All right, that brings us to the end of our presentations for today. I don't think we have anything else up there. Yeah, before closing out today, we want to thank all of our speakers for presenting during today's webinar. We also want to thank everyone for taking the time to attend and for your questions. We hope that you and your family and friends are healthy and safe. Please be sure to fill out and submit the feedback survey for today's event. It should be available to fill out in an email following up. Please note that you can always submit your ideas for any research ideas and innovation ideas that could lead to implementation or deployment at the NJDOT Tech Transfer website.
Yeah, thank you very much, Omid, and thank you very much, Stephanie and her team for arranging the tech talks for us today. And I would like to encourage, as Omid said, so please reach out to our tech transfer website and submit your ideas, your research ideas, innovative ideas, which will benefit NJDOT. So please do share your ideas to us and we will reach out to you as we receive them. So thank you again. Thank you again for the speakers for their wonderful presentations. Have a great day, all of you.
Thank you.
Thank you.